system like a quantum is characterized not just by its Hamiltonian, but also by how I can interact with it, which is Q and P, or something else. So this is
I think that my question has already been asked with his first question, but just to put it again for clarity, I think it's also my neighbour's question, so it may be many people's question. I had the sense that there couldn't be an empirical difference between your view and an Everettian as regards an experiment, at least when you consider not heuristic guesses for the future of physics in further development, but quantum theory as we have it now. And since the relational view was part of quantum tautology, and in fact, happily, the top sentence that we now see states that quantum tautology, a valuable enterprise, is nevertheless not a piece of physics. Would you agree there isn't an observational difference between relational view and Everett?
Yes, completely. I think that, of course, we don't know if quantum mechanics is right? Quantum mechanics could be wrong and it could be superseded by another theory. I think that if it is superseded by another theory, we're not going back to classical theory. It would be something even more strange. But this is just what I think. So I agree that there is no measurement that distinguishes these two ways of viewing things. Completely. Which does not mean it's not interesting, because we are confused about quantum mechanics. So the game here is, can we find a way of thinking about quantum mechanics which is less confusing to us? I think the Bohr is horrendously confusing, because it tells us there's a classical world, but it also tells us the classical world is quantum mechanics. So I think that both many word and the relational view are ways to try to deal with that. I mean, how can the observer be quantum also? We know that in some sense it's quantum. So how to deal with that?
I just wanted to make some comment about this all there is Hilbert space discussion we've been having. I mean, here's what strikes me slightly strange about that way of thinking about it. I mean, there's a sense in which there's no interpretational problem in classical mechanics. The phase space point represents physical reality. Its evolution represents what physical reality is doing. But equally, I mean, it doesn't follow from that somebody committed to classical mechanics in a standard realist way need be committed to the idea that all there is a 2n dimensional space with very little structure on it and a single function on that space and a point that moves in that space. I mean, phase space is a state space. The whole point of the theory is that we represent the entire system under consideration by a single point, and we code all of the other stuff, all of the features of that system in properties of that space, and the way we code it is going to vary from theory to theory. And so it seems similarly in content of something like the Everett interpretation to say Hilbert space is a state space, it's representational, it's just the same straightforward, observer independent, dispositionally independent, whatever way that one wants the classical mechanics is. It's still a state space. All the physical are represented by that point. That point, the evolution is supposed to be doing something physical. Now, a further question, probably a quantum theory dependent question, quite what physical reality is being represented, but that per se doesn't seem to be part of the Everett interpretation, and that per se might well have a different answer in quantum field theory from non-relativistic quantum mechanics, from quantum cosmology, and so on. I mean, and similarly, the project of supposing that we can actually recover everything from the Hilbert space and the spectrum of the Hamiltonian, I think that's an interesting project. It might be right. I'd like to see it being right, but it seems to me that it stands or falls pretty much independently of the Everett interpretation.
Yeah, this is a good question. I think that there is exactly the same discussion in classical mechanics, and I think the same confusion is made in classical mechanics. If you read a book of classical mechanics, you can find in books of mathematicians, more mathematically minded people, a classical system is given by a phase space, defined with a symplectic space up to its symmetry, etc., plus a flow and a Hamiltonian flow. I think that a classical system is characterized by a phase space and a preferred set of coordinates on this space which are physically interpreted. Unless you have those, you can have canonical transformation that kill your physics. And in fact, it's well known in classical mechanics, and it's been discussed, there are papers that discuss that you can take this phase-space Hamiltonian point of view of quantum mechanics and say, I don't remember the case, a harmonic oscillator is the same as a free particle. No, it's not the same as a free particle, because Q and X, Q and P are both chemical configuration, and the custom brackets with Q and H are in the two cases. I agree with what you said, but I would drive it in a slightly different direction. In the old classical mechanics, I think if you want to read everything from the mathematics, you have to specify more about the mathematics. You have to specify Hamiltonian phase-space, the mechanics, and of course the algebra of observable. These are the ones which represent what? Which represent the way you can, if you want, from an instrumentalist operational point of view, but I don't want to be neither an instrumentalist nor operational, of course, what you can interact with the system. So these are the how you tell, and I would say this is the reality of the system. The reality of an electron is to be somewhere at some point, sometimes, and to have perhaps a momentum at some point, sometimes, and not just an abstract point in phase-space without the truth. So, yes, but somehow driving the other direction.
I think we're...
I'm going to start with a quick recap of the background that I gave in the first lecture. So, as I've told you, the sort of key idea in all this is that quantum theory is a special case of a much wider physics, that we're stuck in a certain region where the probability distributions of certain hidden parameters are given by the Born rule, but in principle there's a much wider physics out here, and that the reason we're in here is because of some sort of relaxation process that took place sometime in the past. To the particular hidden variables theory due to de Broglie and further development, in which a system has a certain configuration. Velocity is determined by the gradient of the phase of the wave function. The wave function is regarded as a sort of guiding wave that exists in configuration space. And you get equivalence to quantum mechanics if the initial distribution of these configurations is psi-squared. What do you mean by hidden variables? I'm not sure I explained it terribly well. Wave function in the sense that I can easily prepare a particle given the initial wave function. I put it in a box, I do certain operations, I know the wave function is such and such. What we cannot do is prepare the following. The particle is in the box, its wave function is such and such spread over the box, and the particle is here. We don't know how to do that. We cannot control the initial position. Unfortunately, in this theory, the reason is that the systems you extracted the particle from already had this kind of statistical ignorance in them. Okay, they'd already reached this equilibrium distribution. And if you think this through, if I go in the lab and I pick out an electron from some collection, if this parent ensemble already has a psi-squared distribution, when I put the electron in a box and prepare its wave function, it's going to have this psi-squared distribution with that wave function. You can show these things. So there's a kind of, we're not able to control the initial conditions for these positions when we're in equilibrium, and that's why, in a sense, I think it's fair to call them sort of hidden variables. Anyway, just a detail. Let me now say, and of course illustrating for one particle, as I told you, this pilot wave obeys a Schrödinger equation, which implies the usual continuity equation. If we assume that all particles obey this guidance equation, then a distribution of these particles will necessarily evolve in accordance with this continuity equation. Now, I could begin with any initial distribution P and evolve it forward in time according to this equation. If T happens to equal psi squared initially, then it remains psi squared for all T, because it has the same two differential equations here. And this argument generalizes time scale is comparable. So you imagine if I have an electron in an atom that was a superposition of 16 energy states, the relaxation time scale is going to be the sort of atomic time scales. Okay, so clearly if I want to, if there was non-equilibrium in this system now, and this is some superposition, it's going to very quickly just disappear. But the difference between these distributions can be quantified by this H function. It quantifies the here's rho before I was using P. It's what happens when you recycle slides from different talks. Apologies. But this is the density. Here is psi squared. This is minus the relative entropy of rho with respect to psi squared. It measures the difference. It obeys a coarse-graining H theorem. And in this numerical simulation, in log H against T, this is the coarse-grained H, it decays exponentially. There's an exponential decay of this H function. So this relaxation is a pretty efficient, robust process. And this exponential decay has been verified by other simulations in a variety of conditions for these kinds of systems. Now, when might this have occurred? So presumably it occurred a long time ago. Any system that we have access to, this hydrogen atom in the lab, as I said the other day, it has a history. It has interacted with things. It hasn't just been sitting in a vacuum for billions of years. If this process occurred, it will have occurred way back in time. And so there's a hypothesis here that we could regard quantum noise as a relic of the Big Bang. So let's go back to the Big Bang and see if we can figure out when and how fast this might have happened, and so on and so forth. Okay, so maybe quantum theory, seeing as now inflationary cosmology tells us these hot and cold spots in the CMB are in effect a photograph of quantum fluctuations at very early times, we have a hope of testing the world rule in the very early universe. Okay, that is the recap of basically what I said a couple of days ago, and that only took me 7 minutes, so that's not bad. Okay, so now it's a very mixed audience, so I'm going to give you a 3-minute cosmology crash course. Okay? There are a lot of interesting philosophical questions, I think, in this area. The CMB, how people analyze the statistics, what this theory, how this theory works. And the essentials actually involve very little. You might think it involves a lot of complicated general relativity field theory. So actually, what you the essentials can be understood with remarkably little. For a start, the universe is, to a first approximation, a very good approximation, is flat. Flat and expanding. And this is right back to early times. Now, if you forget about that factor A, this is just the line element of special relativity, proper time relating to coordinate time and the displacement in space. What is standard this factor A is a function of time that's increasing. Tells you the universe is expanding. And it's conventional to take this A to be 1 today. So what you can think of is that today A is 1, and these coordinates X are just your usual physical coordinates today. And T is a time defined by just the average cosmic rest frame. So there is an average cosmic rest frame. Earlier in time, when A is less than 1, a coordinate distance dx corresponds to a physical distance, A of t. So physical distance is smaller in the past. A physical wavelength, let's say I'm talking about some field on space. It might be perturbations in some scalar field or in some density. If I look at it in Fourier space, I'll be talking about modes with different wavelengths. The physical wavelengths also grow with time. And the physical wavelength is just defined to be this. Lambda here is again the proper wavelength today when the scale factor is 1. So please bear this in mind. Physical wavelengths are growing. They're proportional to the scale factor. If I had, for example, a universe where the equation of state is dominated by radiation, you know from the Einstein equation the scale factor will grow as the square root of t. That's, okay, Cosmology Crash Course, Part 1. Cosmology Crash Course, Part 2, the Hubble radius, the important parameter. The Hubble parameter is just defined to be, this is the time derivative of the scale factor, A dot. So it just measures the rate of spatial expansion. And it varies with time. It used to be called the Hubble constant, but it varies with time. It's a parameter. The Hubble radius is just the inverse of that. So for example, if I have a scale factor going as t to the half, the Hubble radius you can work out is equal to A divided by A dot is equal to 2t.